Hello and welcome back. So we left right here where we are discussing searching as a problem in AI. So as we all know, machines are dumb. They don't know what actions to take, what action would be best for them. What they know is that yes, they can compare that if they are on the destination or not, given a true or false. So, without wasting more time, let's dive into it. That uh, how actually we can evaluate a set of algorithms. So, in many cases, when the machine doesn't know for the fact what action might be right for them, it has to take every possible set of option, every possible set of route. Now, this is what we may call later as uninformed search. And so, as a definition of a problem, we have to take these all kind of things into account, which is the initial state, the action we take, which may be a hop to the next city, and a resultant state that after each an action a state changes. So yes, we return that, and a goal test. This is to see that are we have we reached at the destination? Are we fully completed? So that returns a true or false. If it's a false, yes, we'll iterate back. And a path cost or a step cost. So it actually comes from maybe let's say we are making a self-driving car. So a path cost could be the kilometers. It could be the distance kilometers. It could be traffic. It could be um, traffic ingestion, and could be as well as the road quality. Yes, in Karachi we don't have good roads, so yes, that should also be taken into account. Let's move. Yes, here. So we have a few algorithms, but what makes us say that we'll choose an algorithm? So see, for a search tree, what's a search tree is that we have a root node, that is initial state, and then we have children's and a goal node. So each children is basically the state that can be reached through your initial state. You make some action, you go to the children's state, and the goal node is the desired outcome you need to have to reach that goal. But our discussion regarding the algorithm remains the same. Which algorithm shall we choose? What are the performance metric for the algorithm? Which is completeness, that it does find a solution for you actually. Uh, like in all of these, we are sure that it will one or the another day, one or the another time, it will lead us to the destination. Optimality. Optimality is yes, it will take the least amount of time. For here, we know that BFS could be sometimes a greater opportunity for us, and BFS could give us some upper hand in some sort of problems where the solution lies deep in the branch. So yes, a time complexity and space complexity are one few things that we need to be sure when choosing an algorithm, that space complexity and time complexity should be according to our need. Time complexity could be how many nodes are expended and what time it took for the algorithmic execution, while space complexity is about how much memory was used. Like we'll see on that BFS uses queue and DFS uses stack. So these are some sort of memories that we use, right? We'll go and start off with uninformed search, which can also be called as blind search, where the state is known but the action we take, and will it take us towards the direction of the destination, we don't yet know. So this is a type of uninformed search, and the first search example for this is BFS, which is breadth first search. And we can clearly see the fashion is that it move row wise, every row it covers. So what data structure it might be using? It is using queue. Yes. What it does is it pushes an element, then when it marks is visited, like it pushes an A toward inside the queue. Then when it marks A as visited, it pushes the child nodes of the A, which is B and C. We have B and C right here. Now when it will actually go above B and mark it as visited, it will push the children's of B, which is D and E, inside the queue. So Q uses first in first out principle, and that's way how BFS works. It's merely simple, so I'll not waste time on this and go on the DFS thing. Now DFS is the opposite of what we saw here. DFS is basically you will traverse through deep inside the branch and the iterate back when you reach the leaf node. So yes, it is self-explainable, but the data structure we use here is stack. Stack follows last in first out principle. That's the reason the guy that is visited the last, it came out first. So D was visited in the last moment, it is popped out, and E, the other child, is pushed. Hmm. So this is worth reading. That thing is that DFS and BFS, yes, do have a quite difference, but both are blind search. DFS goes into a branch until it reaches the leaf node. So it's not good if the obviously if the goal node lies on the other branch. You have to check each and every depth of the branch, and in the end you will reach towards your goal, which is quite painful. While in BFS, it carefully checks all neighboring children's actually, and it is quite good. The fact if you're feeling the risk that your solution rise on the other end, so BFS could be a great choice at that time. Honestly, it has same time complexity and same um, space complexity as well. So that way, both can be optimal and non-optimal under some circumstances, which is also written right here. Hmm. So for a large tree, a depth first search may take an intensive long time to find even a nearby goal, right? So this way, that DFS won't be helpful and BFS comes in handy. So this is quite explainable. Let's move on to the next. Hmm. Uninformed search. The advantages and disadvantages. So the disadvantages, obviously we know that we have to check all unused data, all unrequired things, and we have to traverse to them, which is quite painful and time consuming. We shouldn't have done this, but since we don't know and our AI agent is not aware of what path it must take, it isn't given the heuristics or the idea that you may proceed at this place and you will reach there. No, it hasn't been given such type of data. It's just a state and it's unaware of the where a state would take it. So technically the environment it has, which is also state, right, it is stochastic. That's the reason we have uninformed search. Now the main issue in that our DFS was that it goes deep inside the branch till the end and it could find um, recurring loops. So that was a big drawback for DFS, for which we introduced depth limited search, where we said that there's a variable called d and we set it as 2. So it will go inside the branch, traverse maximum 2 nodes, and be back towards the top. So this way you don't have the risk of being um, in the recurring loop or things like these. So there's also iterative deepening depth first search, a depth limited search, and Let me just go quickly over here. Well, just to be sure. So it's quite similar to the depth first search but with a limit. We also set the limit here. So what is the depth limited search? Now this is what combines BFS and DFS. It searches to depth 0 root only, then it fails, it reaches to depth 1 and depth 2. Hmm. I'll be back on this. Well, as you may see right here, we have all the complexities right here. So mainly the complexity we need to remember is O b to the power d, which is of this breadth first search, and only a few tweaks will be made in the depth limited search and depth first search, since this guy depends on the number of branches. So just a sec, I have a call to make. Oh god, I have to go in between the video, but what I know is that yes, I have completed the uninformed search. Now what is left is this iterative deepening. Now this is a bit confusing right now for me, but what I know is that depth limited search is what I explained, and it's almost similar to that. Just the difference with that breadth first search and depth limited search are mixed and combined to make something. Alright, so I'll go and pause the video and be right back for the informed search, which is not blind, right? Bye. Bye for now.